Hi everyone, welcome back to the channel. Today we are going to dive deep into a tool which is at the heart of modern software development, that is a CI/CD pipeline. So CI/CD stands for continuous integration and continuous deployment. It's the practice of automating the build, test and deployment phases of a software release process. So every time a developer pushes the code or creates a new change, a series of automated jobs kick off to ensure that the code is stable and gets to the users reliably. So in this video, we'll be designing a multi-tenant scalable CI/CD pipeline for a system like GitHub Actions or a large company like Google, where multiple teams and products use the same pipeline for automating their release process. And throughout the video we'll be using the Git terminology. However, the design choices should be independent of the source control technology. So how would we design a scalable system like this? Let's get to the design. So as usual, first and foremost being the requirements, we need to be clear about what we are building. Let's start with the functional requirements. These are the fundamental features that our system must support. Number one being that our system should listen and consume the events from version control system like GitHub. And whenever a developer makes a git push or creates a pull request, GitHub can send a webhook or an automated notification, and our system needs to be ready to consume it and start the workflow. So listen and consume the events from GitHub. And once our system gets the signal, its next job would be to execute the workflow based on the configuration file. So execute workflow and jobs. So the configuration file typically lives right inside the user's repository, which is a great practice because it versions your workflow right alongside the code. And based on the instructions in this file, our system then executes a series of jobs like compiling the code, running tests, and deploying the application. Additionally, developers will be constantly asking, is my build done yet? Our system must provide a clear user interface where they can see the real-time status of their pipelines, whether they are running, have succeeded or have failed. So our system should provide a user interface for status updates. Additionally, often a successful build produces artifacts which are the result of resulting files like a compiled program, a Docker image, or a test report. So our system needs to securely store these artifacts so developers can download them or use them in later steps of the pipeline. So this one would be store and access the generated artifacts. And next up are the non-functional requirements. So these are the qualities of our system, especially how our system performs under pressure. So first up would be the fault tolerance. That is so what happens if a machine running a critical job crashes? Our system cannot just give up, and it must be fault tolerant, meaning it's resilient to failures and can ideally recover and restart the failed job automatically without losing the progress. So our system should be fault tolerant and recoverable. Additionally, our system will be used by many different teams or companies. So our system should support multi-tenancy, and it is a guarantee that each user's environment is completely isolated. User A's code or data and secrets must not be visible or accessible to user B, and it's a non-negotiable requirement for security and privacy. So our system should support multi with security, privacy, and additionally, what happens when thousands of developers push their code at the same time on a Tuesday afternoon? Our system must be scalable. It needs to handle massive sudden spikes in load without failing over or slowing down for everyone. So our system should be scalable to growing users or developers and repositories. And there you have it. This is our complete blueprint. With these requirements clearly defined, we now have a solid foundation to start our design with. Now that we have designed what our system needs to do and how well it needs to do, let's talk about the specific APIs that serve as the main doorways for information. So our system will be consuming events directly from internal services rather than external client interactions. We do not need a well-defined contract. With that being said, there are two critical APIs that would serve as the primary entry and exit points of information. Number one being the listener API, event listener API. So this API would simply expose a post endpoint. Let's call it V1 close. So when GitHub sends a webhook, it would hit this endpoint, and request would contain important information in the header, request header, like event ID or commit ID, repository ID, client ID, etc. So this will be part of our request body, and the response of this from this API can be a simple acknowledgement with like 200 for status OK, and its source at this endpoint's only job is to confirm that the event is received and received for further processing. And the second endpoint of our system would be is the status API, or to check the status of different workflows. So status API. This API would be used by the developers to check the status of a running workflow, and this can be a simple GET request that client would poll to get the updates. Let's say workflows, and this would be the endpoint. And the client would provide a unique ID for the event, and our service will respond with the current state of the workflow. And the response from our API can look something like a JSON object containing the status of different jobs. Let's say, so it will a response can have like different jobs. Let's say job 1, and job 2, which are currently executing in parallel with status as in progress, and subsequent jobs which are yet to be scheduled, like job 3. This would be waiting, job 4, etc. With these key interfaces defined, we can now start thinking about the scale of our system, which brings us to our next section, that is metrics and estimates. Now we need to understand the scale we are designing for, that is how much traffic our system will get and how much data will store. This is often called back of the envelope calculation, and it's critical for making the right technology choices. So first up, we need to make some assumptions. Let's say that our platform is successful and grows on to handle 100k repositories, and with an average of 10 events per repository per day. And each workflow can trigger on an average of 5 jobs. With these assumptions, let's take a look at our traffic estimates. So how many requests will our system need to handle per second? So we have 100k into 10 workflows per day, which is 1 million workflows per day, and and the traffic per second would be 1 million divided by 10 raised to power 5, which is the number of seconds, estimate number of seconds in a day. So this roughly comes out to be 10 workflow requests per second. And usually the traffic isn't uniform. It spikes during peak hours. Let's assume that peak traffic is 3 times the average, that is 10, and would be 30 requests per second. So this is our right traffic. Developers will be watching for the UI for status updates. Let's estimate the traffic for that, and let's assume that 1% of our daily workflows are running at the same time. average, and so that is around 10,000 workflows running at the same time, and each active workflow is being watched by at least one person, and the UI polls every 5 seconds, and with that we'll have 10k divided by 5, which is 2000 requests per second. So a read traffic for status checks is almost 60 times higher than a write traffic. This tells us that a workflow status service needs for workflow status API or service needs to be incredibly fast, scalable, and it needs to handle a huge amount of traffic. So now let's take a look at the storage estimates. So how much data we'll be storing? Let's break down the data into two pieces. One is the metadata, which is the data about our workflows and jobs. So we have 1 million workflows per day. Let's say that each record is about 1 KB. And that's about 1 GB of data per day. Data which is like 1 million into 1 KB. So each workflow now has 5 jobs, which is 5 million jobs per day, and let's say that each record is 2 KB, that is around 10 KB, 10 GB of storage per day for the jobs. So our total metadata will be 1 GB plus 10, which is around 11 GBs per day. And let's say in our system we keep this data for 90 days, and with this we'll have 11 GB into 90, and it should roughly come out to be 1 terabytes of storage. So this storage capacity is well within the limit of modern distributed databases like DynamoDB or Cassandra. Additionally, our system will be generating a lot of artifacts and logs. So this is where the real volume of our system's storage would be. And having an estimate for that, let's say for logs, we generate 5 million, we have 5 million jobs running per day, and let's assume on an average our log size is 1 MB per job. So that's around 5 TB of log storage per day, and artifacts with 1 million workflows per day, assuming around 10% of the workflows generate artifacts, with an average size of 100 MB. With this we have around 1 million into 10 MB, which is roughly around 10 TB of storage per day. And so this would mean a total storage of 15 TB for logs and artifacts, and which is roughly around 15 TB into 365 per year, which roughly comes out to be 16 petabytes. Now, as massive as these storage numbers are, they don't even touch on the biggest and most expensive part of our system, which is the compute resources. So the traffic and metadata storage are tiny compared to the compute resources needed for actually executing the jobs. Based on our estimate, we have around 100k workflows executing at any given time. And this means that we need a massive and scalable, efficient pool of executors ready to handle this load. Therefore, the most significant part of the entire design is ensuring that we can scale our compute resources effectively. And this is where most of our cost and complexity will be. And from my experience at Google, I can give you a real world idea of how just significant this number is. A major CI/CD infrastructure can have rough operational costs roughly equivalent to the salaries of 34 software engineers. That's how massive the compute cost of the compute and compute resources are. So these estimates give us a clear sense of scale and directly influence our architectural choices. Keeping these numbers in mind, let's move on to the next section, which is the high level design. So let's start with the simple and high level design for our system, which satisfies our core functional requirements. So our workflow would trigger when a developer pushes the code, and will receive this event from the source control or GitHub. Let's say this is our source control, and so when a developer pushes the code, GitHub or the source control would send out an event notification, which will be received by our entry point, that is the event listener API, or the first endpoint which we exposed in our APIs. Event listener service. Now this event listener service would be just a lightweight service, and its main job is to be incredibly fast, that is catch the incoming event and perform a quick validation and store it in some message queue for processing. And once it writes to this queue, it will simply send an acknowledgement and simply send an acknowledgement back to our source control. And critically, it doesn't do any heavy lift work itself. Instead, it just stores the event in the queue for processing and ensures that our front door listener to the events is never blocked and can handle thousands of requests without slowing down. Now the core functionality of our system would be performed by this service which consumes the events from this queue, and let's call it workflow executor service. So workflow executor service would be the brain of our system, and this service will consume the events from this queue, and it needs to figure out what needs to be done by pulling the configuration file from the repository, and see what the list of jobs that need to be executed, like build, test, or deploy. And to keep track of everything, this executor service needs some memory, and which will be our database. And this workflow executor would connect to this database and create a record for this new event workflow, which would be a unique event ID. So we'll have workflows table which will have the event ID, and this can be our primary key, and other details like repository ID, client ID or tenant ID, and any other metadata, status of the job, status of the workflow, etc. So our workflow executor service would store this information, and additionally it parses the configuration file and maps out all the jobs that need to be run and their dependencies. And this information would be stored in the database as well. Let's say in a separate table, let's call it jobs table, and it will have the ID of different jobs that need to be executed, event ID or the workflow event ID of the workflow that the job is part of. Additionally, some of the jobs may be dependent on other jobs in the workflow to complete, so each job will have a parent ID associated with it, so that once all the parent jobs have completed, once the parent job has completed, the execution for that job can start. And similarly, we'll have a status field for this. So the database will be the single source of truth, and the workflow executor service constantly updates it with the workflow status as and when the different jobs are executed. So our workflow executor is the brain, but it shouldn't do the heavy lifting itself. If it did, it would become a bottleneck, and instead it delegates the actual work to a team of workers. Let's call it job executors, and let's say we'll have multiple job executors. These are job executors, and So our workflow executor service will check with an available job executor and delegates the actual work to that executor. And when a job is ready to run, the workflow executor service based on this plan will send request to one of the available executors, and these executor and they will actually these executors will do the actual work, that is spin up a clean and isolated container. They'll check out specific version of the code and run the commands defined in the workflow file. And we can have a pool of these workers allowing us to run hundreds of builds in parallel, and this is what would make our system truly scalable. And as these jobs run, they can produce two important things: logs and artifacts, as we discussed. We can't just leave these on the worker machine, because these machines would be temporary. The jobs are running in a container, so we need a durable and central place to store them. For that, we can use an object storage like S3. And object storage like S3, and we can so once the job executor runs the job, it constantly streams the logs to this storage bucket, and when the job is done and an artifact has been created, the executor uploads that file to the bucket as well, and it then gets back the original URL for the log file and the artifacts, and save this information in our database. So our workflow executors will be updating the database, and this information can be stored right next to the job record with S3 URLs for the buckets, and this way we have a permanent and secure record of everything that happened. Now our system is running the jobs and storing the results. So once the job execution completes, it also needs to notify the workflow executor that this job is complete, and the workflow executor can subsequently start the next job upon completion. So this will be a two-way communication between job executors and workflow executor service. Upon completion of jobs, workflow executor will check will mark this job status as complete, and will check for the remaining jobs in the for this ongoing workflow, and will find the next job that needs to be executed. If there is a job that needs to be executed, the workflow executor service will then post it again to one of the available executors. And once this process completes and there is no all the jobs have been completed, the workflow event can be marked as completed. So this is how our system will be running different jobs and executing workflows. But also our developer needs to see, wouldn't know any of this. So we need a window into our system for developers to view this information. And for this, we'll create another component, and let's call it workflow status service. Let's and so this is what a developer or client will this service what a developer or client will connect with. And this status service, when a user opens their dashboard, will query a database. So since the database is the source of truth, and it will check with the database and send back the latest information, including the links to the logs and artifacts that we stored. And we keep this a separate service to ensure that the lot of users who are checking the status won't slow down the core work running the builds. And with this, yeah, we have the basic functional design. And let's step back and take a look at what we have drawn. We have a complete high-level architecture with clear separation of concerns, a fast entry point, and a central orchestrator, and a scalable pool of workers with durable storage, and a dedicated service for users to check the status. But this design isn't complete yet. How does our system handle failures, and how do we scale our system to multiple workflows? And this is what we'll discuss in the next section, which is the deep dives. Our high-level design works well under normal circumstances, but as engineers, we must also plan for when a component fails. Right now, our workflow executor service directly tells the job executor to run a job. If the executor's machine crashes during a critical deployment, the job is simply lost, and there is no way for the workflow executor service to recover from this state. And this is not acceptable for a reliable system. This direct communication is fragile because it assumes that the executor will always be available, and to make our system fault tolerant, we need to remove this dependency. We'll do this by introducing a message queue. First, let's change a diagram. I'm going to erase the direct arrows from workflow executor to the job executors. And in this place, we'll draw our first new component, that is the jobs queue. Now the workflow executor no longer directly talks to these job executors. Instead, it packages a job into a message and places it onto this queue. And the job executors now act as a pool of consumers, constantly watching the queue and picking up the jobs whenever they are free. So this will be the structure. And this change significantly improves our system's reliability. Let's see how. So how does this queue prevent us from losing jobs? It uses a mechanism with message queues, that is the visibility timeout. So here's how it works. A job executor pulls a job from the queue. The queue doesn't delete the message, it just makes it invisible for other executors to and starts a timeout clock, let's say for 10 minutes. The executor essentially has leased this job. Its normal process occurs, the executor finishes the jobs. If the normal process occurs, the executor finishes the job and sends an acknowledgement to this to the queue, and when and this acknowledgement then permanently deletes the message. But if a failure occurs, the executor or the executor crashes, it can never send that signal. The queue waits, and after 10 minutes the timeout expires and it realizes that job never completed. it then makes the message visible again and ready for another executor to pick up and retry. With this method, no jobs are ever lost, and we get automatic retries, which provides a guarantee known as at least once delivery. Now we've made the jobs dispatching reliable, but there is another point of failure. How does the job executor report its status, success or failure back to the workflow executor? And if the executor calls this workflow executor service directly, we have the same fragile connection problem again. The workflow executor service might be busy or temporarily down. This the solution is the same pattern. We'll use another queue, and let's draw the second queue between the executors and the brain of our system, which is the workflow executor service. Sorry. This is our jobs queue, and this would be the status queue. And so once a job executor finishes its work, it places status update messages into this status queue. So it will be like this. And the workflow executor service will consume messages from this queue, and when it sees a job has succeeded, it updates the database and schedules the next job in the plan. By using the second queue for status updates, we have created a fully asynchronous and reliable two-way communication channel between our workflow orchestrator and our actual workers. And the entire system can now withstand failures at any point without losing data or halting the progress. So we have made our worker communication extremely reliable with the jobs queue and the status queue. But let's take a step back and talk about the very first queue, the one that receives the initial trigger from our API service. And a crucial question for reliability is how long should we keep the initial event message before deleting it in the events queue? Do we have to wait for the entire workflow, which could take hours to complete? The answer is no, and our design explains why. Let's walk through the life cycle of that first message. The workflow executor pulls an event from the events queue. Just like the other queue, a visibility timeout starts. The system now has limited time to process the initial message. Next, the executor service performs its critical setup work, that is reads the event, fetches the workflow configuration file from source control system, parses it, and builds a complete execution plan and updates the database. Finally, it looks at the execution plan and dispatches the first set of jobs by placing them on the jobs queue. And this is the most important step. Once the plan is safely stored in a database and the first jobs waiting are in the jobs queue, the responsibility of that initial message is now over. The state of the workflow is no longer just stored in this one message. It's now durably persisted in our database and the jobs queue. So At this point, the workflow executor service can send an acknowledgement back to the events queue, which can now safely delete the original message. We do not need to wait for the whole executor workflow to finish, because from this point on, the workflow is driven reliably by a feedback loop. The jobs are picked from this jobs queue and their completion status is sent to the status queue, which is what triggers the subsequent jobs. By strategically introducing message queues, that is jobs queue and for dispatching the work, and status queue for reporting back, we have transformed our simple design into a truly resilient system. The core principle here is decoupling. Our services no longer have fragile direct connections. Instead, they communicate asynchronously through these durable queues. And this is a powerful pattern you'll see in almost every large-scale distributed system. So we have built a system that's fault tolerant and can recover from failures. Now we have to tackle one of the most important aspects of our shared service, that is multi-tenancy. So multi-tenancy is the principle that a single instance of our software serves many different customers or tenants, and in case of Google, multiple teams within a Google. And think of, say, a CI/CD system like an apartment building. We own the building, the infrastructure, and we have many tenants like teams from Volvo, Polestar, and Renault, all living in and working in it. Responsibility as a landlord is to make sure that what happens in one apartment is completely separate from what happens in another, and this gives us two primary jobs. One is data isolation, that is make sure no client or tenant can look into their neighbor's apartment, and another is the resource isolation, which is to make sure one tenant's loud party or a resource hungry job doesn't disturb the neighbors and doesn't leak, our system doesn't leak any information of one customer to the other customer. So let's break down how we achieve it. First, let's talk about data. How do we ensure that different customers cannot see the build logs, source code, or secret keys from each other? The answer is how we design our database. When the workflow executor service writes information about a workflow, it doesn't just throw it all in one giant table. Every single row in the database must have a column that identifies who it belongs to, and we can call it client ID or tenant ID, and this client ID would be used as the partition key. Or shard key. And this tells the database to logically group all the data together for one tenant together, and think of it like a color coding scheme for folders in a giant filing cabinet. All of the Volvo's folders are blue and Renault's are red. Even with this system, like blue and red folders might end up in the same physical drawer. Data for two different customers can absolutely live on the same physical machine in the database cluster. So how this is secure is the database system itself acts as a strict guard, because we use tenant ID as the partition key. The database software layer enforces a wall between the data. So when our application asks for all the blue folder, the database's logic makes it impossible for it to accidentally grab a red one, and even if they are stored side by side, this logical separation is then backed by a strict rule in the application's code. Every single query to the database, every request for data must include this client ID or tenant ID in the request, And this combination of database level logical separation and application level discipline is what makes it virtually impossible for one client's data to leak to another. So we have secured the data while it's sitting in the data, but what about when jobs are actually running? This is where resource isolation comes in. We can't let a poorly written build script from one tenant use up all the CPU on a machine, starving every other tenant's build. And this is the classic noisy neighbor problem. Even worse, we can't allow one job to access the file system and read the files of a different job running on the same machine. The solution here is containerization. So a job executor machine doesn't just run jobs in side by side in its operating system. That would be a security nightmare. Instead, every job it pulls up from the jobs queue, it spins up a brand new completely isolated container. So basically each worker will actually spin up a container and job executor machine doesn't run jobs side by side on its operating system, and each job would be run in a container, and we can use technologies like Docker, and this container acts like a secure private room for the job to run in. The container has its own private file system. The code resides inside it, can't see any files of on the host machine or on other containers, and it's in its own little world. We can configure each container with strict limits. We can say the job is only allowed to use 2 CPU cores and 4 GB of RAM. If it tries to use more, it's automatically throttled or terminated, which prevents one job from being a noisy neighbor. As soon as the job is finished, the container is completely destroyed. The next job starts when from a fresh clean state, ensuring no secrets, files or settings are accidentally leaked from one job to the next. So by combining these two strategies, a strict data partitioning scheme in our database and an ephemeral resource limited container, we have built a robust multi-tenant system. We've given each tenant their own secure, private and soundproof apartment within our building, and this is absolutely critical for building trust and providing a stable and predictable service for all our users. We have designed a system to be fault tolerant and secure with multi-tenancy, but can it handle a massive increase in load? And this brings us to our last non-functional requirement, which is scalability. Scalability means that as we add more users and more repositories and concurrent builds, our system's performance must not degrade. If 100 developers are using our system today, it should work just as well when 10,000 are using it next year. So where is the primary bottleneck in our system? It's the actual execution of the jobs, that is builds and tests, and which are our job executors, and this is where the real work happens, and it's where the most demand will be. So how do we scale it? The key to our strategy would be horizontal scaling. This means instead of just making one executor bigger and more powerful, which is vertical scaling and has limits, we just add more identical executors to the pool. Each executor is a stateless worker designed to do one thing: pull a job from the queue and run it. Because they are stateless, we can add or remove them at will without disrupting the system. If thousands of jobs come in, we can spin up new executors to handle them. and we can do this automatically with auto scaling, and which is directly tied to our jobs queue. So the system constantly monitors the number of messages waiting in this queue, which is called the queue depth, and we can set up a simple rule. If the jobs queue depth goes above 100 waiting jobs, automatically launch 10 new job executor instances, and as new instances come online, they immediately start pulling jobs from the queue and the line gets shorter. And the reverse is also true. The ability to scale both up and down is called elasticity, and we can set another rule. If the jobs queue is near zero for more than 5 minutes, terminate 10 idle job executor instances. This way our system can add resources to meet the demand and remove them to save costs when things are quiet, and it's incredibly efficient and responsive. So we'll have a monitor for our jobs queue. So job executors are the main story, but what about the other services? So our event listener service and the status workflow status services, these are lightweight stateless web services. We can easily run multiple instances of them behind a load balancer to handle as much traffic as we need. And a workflow executor service, this service can be scaled horizontally as well. We can have multiple instances pulling from the events queue to process different workflows in parallel. And the database, which is often the trickiest part to scale. So for a high read traffic from workflow status service, we can have read replicas. And remember a decision during multi-tenancy discussion to use tenant ID as the partition key. This not only isolates the data but also sets up perfectly for future database scaling like sharding if a write load ever becomes a problem. So as you can see, like scalability wasn't an afterthought. The decisions we made earlier, that is separating services, using queues for decoupling, and designing a database schema for multi-tenancy, all contribute directly to making this system architecture that's built for growth. And with that, we have designed a complete CI/CD system from ground up, tackling exactly the way you do in a real interview. So what are the key takeaways? If there is one thing that I would like you to remember is start with a simple design. Don't try to build the most perfect and complex design from day one. Instead start with the design satisfying the core functional requirements with a simple architecture, and once you have a solid foundation, then iteratively add support for complex features using message queues to tackle our non-functional requirements. It's about evolving the design and not starting the perfect design from day one. So I hope this video gives you the confidence and the structured framework to tackle your next system design interview. If you find the video helpful, please give it a thumbs up and subscribe to the channel for related content. And please do share in comments if there is any design that you would like me to cover next. Thank you for watching the video.